Physicists ran the numbers on why the universe exists. The math says it shouldn't. Not a rounding error, not a footnote correction that gets fixed in the next model. A flat, total mismatch between what the equations predict and what's actually sitting here, holding together well enough for you to read this sentence. Right now, you're sitting inside a universe balanced on a razor's edge. Nobody voted on this. Nobody designed it, at least not in any way physics can prove. It just came out this way. Numbers landing in the one narrow lane out of an almost infinite highway where atoms hold together, stars ignite, and something eventually sits up and starts asking questions about it. 5 numbers make this possible. 5 suspects, 5 separate branches of physics, each one measured independently, decades apart, by people who weren't looking for a pattern. Dark energy. The mass of the Higgs boson, the strength of the force binding every atomic nucleus in your body, the tiny leftover imbalance between matter and antimatter, and the flatness of space itself. Here's the case file's opening statement, plain and simple. Move any one of these past a decimal point. Not a huge shift, just a nudge. And there are no atoms, no stars, no galaxies, no you, no me, no planet to stand on while asking why. Physics has a name for this: fine-tuning. And the deeper you dig into each of these 5 numbers, the less it looks like coincidence, and the more it looks like something physicists genuinely do not know how to explain. Prepare yourselves. We begin. Albert Einstein is sitting with his own equations, and they're telling him something he refuses to believe. He had just finished general relativity, the theory that would define gravity for the next century. But when he ran the math for the universe as a whole, it gave him a universe that couldn't sit still. It had to be expanding or contracting. No stable middle ground existed in the numbers. Every astronomer alive in 1917 believed the universe was static, fixed, eternal. The stars had always been there and would always be there, unmoving, unchanging. So when Einstein's own theory told him otherwise, he didn't trust the theory. He trusted the assumption. He went back into his equations and added a term, a built-in pressure baked into empty space itself, pushing outward, strong enough to cancel out gravity's inward pull and hold the whole universe in perfect balance. He called it the cosmological constant. It wasn't a discovery. It was a patch, bolted on for the sole purpose of forcing the math to agree with what everyone already assumed was true. For over a decade, that patch held. Then, in 1929, Edwin Hubble pointed a telescope at distant galaxies and found they were all racing away from us, not drifting, racing. And the farther away a galaxy sat, the faster it was receding. The universe wasn't static at all. It was expanding, exactly the way Einstein's original equations, the ones without the patch, had said it would. Einstein looked at what he'd done and reportedly called it the biggest blunder of his career. He'd invented a fix for a problem that didn't exist, bending his own breakthrough to match a belief that turned out to be wrong. He pulled the constant back out. For most of the 20th century, it sat in physics history as a cautionary tale, proof that even the greatest scientist alive could talk himself into fudging the numbers. Here's where the story should have ended. A mistake, corrected, filed away. It didn't end there. 70 years later, a completely different group of scientists, chasing a completely different question, found something in the data that made no sense under any existing model. And when they went looking for a term that could explain it, the only thing that fit, the only piece of math that matched what they were seeing, was the exact same fudge factor Einstein had thrown away in embarrassment. The blunder didn't just come back. It came back as the leading explanation for one of the strangest discoveries in the history of cosmology. And it brought a number with it. A number so disconnected from anything physics expected that, once you understand what it actually says, you start to wonder if calling it a blunder the first time was the only part of this story that ever made sense. Here's the number. Quantum mechanics predicts a value for dark energy that is 10 to the power of 120 times larger than what we actually measure. Sit with that for a second, because it's easy to read a number like that and let your eyes slide right past it without feeling the weight of it. 10 to the 120 isn't a big number in the way that the national debt is a big number, or the distance to a far galaxy is a big number. Those numbers are enormous, but they're the kind of enormous your brain can still gesture at. This is a different category entirely. Try this instead. If you tried to write that number out in full, every zero taking up one digit of space, you would run out of atoms in the observable universe before you finished writing the zeros. There aren't enough particles in existence, all of them, every proton and electron in every star and galaxy, to represent that number as a simple count. That's the size of the gap between what our best theory of the very small says should be true, and what our telescopes say actually is true. Here's how physicists get there. Quantum field theory says, empty space is never really empty. Zoom down far enough and you find particles flickering in and out of existence, popping up from nothing and vanishing again, faster than anything can register them directly. Each one of these flickers carries a tiny bit of energy. Add them all up, every field, every possible particle, all the way up to the highest energy scales physics currently trusts, and you get a number for how much energy should be packed into every cubic inch of so-called empty space. Now compare that number to the actual measured strength of dark energy, the thing that's accelerating the expansion of the universe right now. They don't just disagree. They disagree by that impossible margin, 10 to the 120, a gap so extreme it doesn't even function like a normal scientific disagreement anymore. It's not two experiments giving slightly different readings that need reconciling. It's one theory saying the sky should be a specific color and reality showing up completely colorless instead. Play out what would happen if the quantum prediction were actually correct. If empty space really carried that much built-in energy, the outward push would be so overwhelming that space would rip itself apart in a fraction of a second. Not slowly. Not over billions of years the way dark energy is stretching the cosmos today. Instantly, before a single proton could find a neutron, before the first atom had any chance to form. No stars, no galaxies, no universe old enough to cool down and build anything at all. That obviously isn't what happened. You're proof of that, which means something in nature is cancelling out almost the entire predicted value. Some mechanism reaching in and subtracting nearly all of that energy, leaving behind only the sliver that lets a universe like ours exist. This is why physicists don't hedge when they talk about this one. They call it the worst theoretical prediction in the history of science, and they mean that literally, not as an insult, but as a technical description. No other calculation in physics misses its target by anything close to this margin. Something is doing the cancelling. Nobody has ever caught it in the act, and nobody has a working theory for what it even is. Picture a dial, one single dial, and it controls exactly one thing: how strong dark energy is, how hard it pushes outward against the pull of gravity. Turn that dial up even slightly past the value we actually measure, and here's what happens in the early universe. Matter is trying to clump together. Hydrogen gas drifting through the young cosmos needs gravity to grab hold of it, pull it inward, compress it until it gets hot enough and dense enough to ignite a star. That process takes time. It needs regions of space to sit still long enough for gravity to win a very slow, very patient tug of war. Crank up dark energy's push and that patience runs out. Space stretches faster than gravity can organize anything. The raw material for the first stars gets flung apart before a single clump can form. No stars means no heavy elements, because every element heavier than hydrogen and helium gets forged inside a star. No heavy elements means no rocky planets, no carbon, no oxygen, nothing on the periodic table that a body could be built from. Turn the dial up, and the universe stays a thin, cold mist of gas forever. Now turn it the other way, weaken dark energy, dial it down below the value we observe, and gravity stops having to fight for anything. It wins immediately. Instead of a careful, billions of years long process of matter gathering into galaxies, everything collapses back on itself almost as soon as it starts expanding. The universe doesn't get a slow burn. It gets a rapid implosion, falling back into a single dense point within the first fractions of a second after the Big Bang, before atoms even finish forming, let alone stars or galaxies or anything resembling structure. There's no long cosmic history in that version. There's barely a universe at all, just a flicker and a collapse. So the dial has exactly one narrow position where both of those disasters get avoided, strong enough to let the universe expand and cool without gravity, forcing an instant collapse, but weak enough that gravity still gets to do its slow work, pulling gas into stars and stars into galaxies before the expansion pulls everything too far apart to interact at all. That's the window we're sitting inside. Not a wide, forgiving range where lots of possible values would have worked fine. A narrow lane bordered on one side by a universe that never builds anything, and on the other side by a universe that crushes itself before it starts. This is the part where physics usually offers you an explanation, and this is the part where it doesn't. Nobody has a mechanism that forces the dial to land in that lane. No symmetry, no law, no deeper equation that says the number has to be this value and not some other one further up or down the scale. It's just where it landed. And once you sit with that fact, physicists split into two camps. One camp says there has to be a reason we haven't found yet, some deeper physics still waiting to be uncovered that pins this number down the way other constants get pinned down by underlying theory. The other camp says maybe there isn't a reason at all, at least not the kind you can derive from an equation. Maybe the only explanation is that in a large enough collection of universes with different dial settings, we could only ever find ourselves in the one narrow lane that didn't collapse or blow apart before we existed to look. That second idea has a name, and it's going to come back later in this investigation. For now, the case file moves to a different suspect, one that isn't hiding in the vacuum of empty space at all, but sitting inside a particle discovered in a tunnel under the border of France and Switzerland. July 4th, 2012. A conference room at CERN, scientists standing up to announce they'd found it. The Higgs boson, the particle that gives every other particle its mass, confirmed after almost 50 years of searching. It was treated like the closing of a case, the last missing piece of the standard model finally slotted into place. Except it wasn't a closing. It was the moment the case file cracked back open in a different direction, because the mass they measured for that particle was, by every reasonable calculation physics had, a number that shouldn't have been possible. Here's the problem, and it's called the hierarchy problem. The Higgs boson has a mass, roughly 125 times the mass of a proton. On its own, that number means nothing to you. But quantum mechanics doesn't let a particle's mass sit quietly at whatever value it wants. Every other particle in existence is constantly interacting with the Higgs field through what physicists call quantum corrections, tiny nudges from virtual particles popping in and out of existence, each one tugging on the Higgs mass a little. Add all of those tugs together, all the way up to the highest energy scale physics trusts, and the Higgs mass shouldn't sit anywhere near 125. It should get dragged up, relentlessly, toward a number 17 orders of magnitude higher. That number is called the Planck scale, and it's worth holding in your head for a second, because everything about this case file depends on the gap between it and where the Higgs actually sits. Think of the Planck scale as the energy where gravity itself stops behaving politely and starts demanding a quantum theory nobody has built yet. The scale where the Higgs boson actually lives. The electroweak scale is the energy where atoms, forces, and chemistry, as you know them, operate. The distance between those two scales isn't like comparing a mile to 1,000 miles. It's like comparing the width of a single atom to the width of the observable universe. That's the size of the canyon quantum corrections should have pulled the Higgs mass across. Physicists have a word for what a number is supposed to look like when nothing special is protecting it. They call it natural. A natural number sits at whatever scale its underlying physics points to. No fine cancellations required. No suspicious precision. Most particle masses in the standard model get this kind of protection from an underlying symmetry, something that keeps quantum corrections small and well-behaved, no matter how high you crank the energy scale in your calculation. The Higgs doesn't have that protection. Nothing in the standard model shields its mass from those corrections. Left alone, the math says it should be enormous, dragged up toward the Planck scale by forces with no reason to stop pulling. And yet here it sits, small, stable, parked at exactly the value needed for atoms to hold together the way they do in your body right now. Nothing protects this number, and it landed exactly where it needed to land anyway. Run the calculation forward. Let quantum corrections win. Let the Higgs mass actually sit where the math says it should, dragged up near the Planck scale, instead of parked at 125 proton masses. Here's what that universe looks like. The Higgs field isn't some isolated piece of machinery sitting off to the side of physics. It's the thing that gives mass to the W and Z bosons, the particles that carry the weak force, and it's the thing that gives mass to every fermion, every quark, every electron, through its interactions with the Higgs field. Push the Higgs mass up toward the Planck scale, and you don't just change one number in isolation. You drag the W boson mass up with it. You drag the Z boson mass up with it. You drag the mass of every electron and every quark in existence up along the same climb, because all of those masses are set by how strongly each particle couples to the Higgs field. And the overall scale of that field is exactly what just got dragged to a completely different neighborhood of the universe. Electrons that heavy don't sit in orderly shells around a nucleus the way they do now. The whole architecture of the atom depends on a careful balance between how strongly the nucleus pulls and how the electron settles into place around it. Push electron mass up by that many orders of magnitude, and you don't get a heavier version of hydrogen. You get something that doesn't hold together as an atom at all, in any recognizable sense. No electron shells arranged the way chemistry needs them arranged. No shared electrons forming bonds between atoms. No molecules built from those bonds. No periodic table, because the periodic table is really just a map of how electrons settle into place around nuclei of different sizes, and that whole map depends on the masses staying where they actually are, not where the raw calculation says they should be. Stated plainly, a Higgs mass at the Planck scale gives you a universe with no chemistry. Not worse chemistry. No chemistry. Nothing resembling matter as you understand it. No atoms stable enough to combine into anything more complex than a very short-lived mess of particles. Physicists went looking for something that could stop this from happening. Some mechanism that protects the Higgs mass the same way an underlying symmetry protects other particle masses from getting dragged around by quantum corrections. The leading candidate had a name: supersymmetry. The idea proposed a partner particle for every known particle, a shadow version of the electron, a shadow version of the quark, each one carrying opposite quantum statistics from its counterpart. Run the correction calculation with those partners included, and their contributions cancel out almost the entire dangerous pull toward the Planck scale, leaving the Higgs mass stable right where it needed to be. For this to work, though, those partner particles couldn't be hiding at some impossibly high energy no one could ever reach. To actually cancel the correction cleanly, they needed to show up at an energy scale physics could test directly, somewhere around the TeV range, well within reach of a large enough particle collider. Physics built exactly that collider. It searched exactly that range. And it found nothing. Before the Large Hadron Collider ever switched on, there was a kind of quiet confidence running through the field. Not certainty. Physicists are trained out of certainty, but something close to it. Supersymmetry wasn't a fringe idea. It was the leading candidate, the mechanism most theorists expected to actually show up once you built a machine powerful enough to look. The prediction was specific enough to be exciting. If supersymmetry protected the Higgs mass the way it needed to, its partner particles couldn't be hiding at some remote energy scale. They had to sit close, within reach of the collider's power, or the cancellation wouldn't work cleanly enough to solve the problem in the first place. Squarks, the partners of quarks. Gluinos, the partners of the particles that carry the strong force. Neutralinos, candidates that also happen to fit neatly as a dark matter particle, solving two mysteries with one discovery. Physicists built detector systems specifically tuned to catch the signatures these particles would leave behind if they existed anywhere near the predicted range. The machine ran. The data came in, collision after collision, year after year. None of them showed up. Not squarks at the expected masses. Not gluinos. Not neutralinos. The collider kept pushing its search to higher and higher energies, and the superpartners kept failing to appear, again and again, in exactly the range where the theory needed them most. This didn't kill supersymmetry outright. What it did was worse, in a way, because it created a problem inside the very theory that was supposed to solve a problem. If the partner particles exist at all, they now have to sit at a much higher mass than originally predicted, pushed up by every null result the collider produced. But push those masses up too far, and the cancellation that was supposed to protect the Higgs stops being clean. You need some tuning again, smaller than the original hierarchy problem, but tuning all the same. Physicists call this the little hierarchy problem. A smaller version of the very crisis supersymmetry was invented to close, now sitting quietly inside its own best solution. Other ideas tried to fill the gap. Technicolor proposed that the Higgs wasn't a fundamental particle at all, but a composite, built from a new kind of strong force, acting at a much shorter distance. Composite Higgs models followed similar logic, treating the particle discovered in 2012 as a bound state rather than something elementary. Both approaches avoided the original hierarchy problem in their own way. Both ran straight into a different wall: precision measurements of the Higgs boson's properties, how it decays, how it couples to other particles, kept coming back, looking almost exactly like the simplest, most vanilla version the Standard Model predicted. Any theory that wanted the Higgs to be composite had to explain why it behaves so convincingly like it isn't. Here's where the field sits right now. The mainstream fix for one of physics' oldest fine-tuning problems went looking for its supporting evidence at the one machine built specifically to find it, and came back empty-handed. Some call this a naturalness crisis, a moment where the guiding principle that told physicists where to look for decades just failed its biggest test. Nothing has replaced it yet. Zoom past the electron, past the nucleus wall, down to the space where protons and neutrons sit, crammed together closer than anything else in nature allows. Something is holding them there. Protons all carry positive charge, which means they should be shoving each other apart with tremendous force. Every nucleus in every atom in existence should be flying apart the instant it forms. It doesn't happen because a separate force takes over at that distance, one strong enough to overpower electric repulsion completely. Physicists call it, without much poetry, the strong nuclear force. It's the thing binding every proton and neutron together inside every atomic nucleus that has ever existed, including the ones in your own body right now. This force works over an almost absurdly short range. Step outside the nucleus by even a small amount and its grip vanishes almost entirely. But inside that tiny space, it's the strongest force in nature by a wide margin, and its exact strength turns out to matter enormously. Turn that strength up, even slightly, and the consequences hit almost immediately. Two protons that would normally need to overcome their electric repulsion and rely on a delicate balance to bond, suddenly fuse together far too easily. Hydrogen, the simplest element, the raw fuel every star depends on, stops existing as a stable standalone atom. It gets swallowed into fusion before it ever has the chance to just sit quietly as hydrogen. Stars burn by fusing hydrogen slowly, patiently, over billions of years, releasing energy at a manageable rate that lets a star shine steadily instead of detonating. Crank up the strong force and that patience disappears. Fusion runs away almost instantly. Stars don't burn the way they do. They burn the way a bomb does. Now turn the dial the other direction. Weaken the strong force even slightly, and the opposite disaster shows up. The force that holds multi-proton nuclei together starts losing the tug-of-war against electric repulsion. Deuterium, the first step on the ladder toward building anything heavier than hydrogen, stops forming at all. Without that first step, the entire chain breaks. No helium, no carbon, no oxygen, no iron. Every element on the periodic table past hydrogen exists because nuclear fusion inside stars managed to bind protons and neutrons into heavier and heavier configurations. And every one of those bonds depends on the strong force sitting exactly where it sits. Weaken it, and that ladder never gets built. The universe stays a thin haze of hydrogen, nothing else, forever. The range that avoids both disasters isn't generous. It's a narrow strip between a force strong enough to make stars detonate and a force too weak to build anything past the simplest atom in existence. Nudge it either direction by a small percentage, and the entire chain of stellar chemistry that produced every heavy atom in your body simply never happens. That would already be enough to close this case file on its own. But the strong force carries a second mystery, buried inside it, one that has nothing to do with fusion or stellar burning, and everything to do with a basic symmetry of nature that physics allows to break, and that, for reasons nobody can explain, refuses to. Physics has a rule about symmetry, and the strong force is allowed to break it. Nothing in the equations says it can't. Charge conjugation and parity, combined into what physicists call CP symmetry, describe a basic expectation that the laws of physics should look the same if you flip every particle into its antiparticle and mirror the whole system in space. The weak force breaks this symmetry, and physicists have measured that breakage directly in decaying particles for decades. The math governing the strong force contains a term that would let it break the same symmetry too, a built-in angle physicists call theta, free to sit anywhere between 0 and a full circle. It doesn't sit anywhere. It sits as far as anyone has ever been able to measure, at 0. Not close to 0, not small enough to round off, as close to dead 0 as any measurement in physics has ever pinned a number down. Here's how physicists caught it in the act, or rather, how they caught it not acting at all. Picture the neutron, sitting neutral in charge, but built from 3 charged quarks arranged inside it. If the strong force actually violated CP symmetry the way its own equations allow, that violation would show up as a tiny separation between positive and negative charge inside the neutron itself, a property called an electric dipole moment. A neutron with a lopsided internal charge distribution would behave ever so slightly, like a compass needle in an electric field, twisting to align itself in a way a perfectly symmetric neutron never would. Physicists built experiments sensitive enough to detect exactly that kind of twist, storing neutrons in precisely controlled fields and watching for any hint of alignment that shouldn't exist if CP symmetry holds. They found nothing. Experiment after experiment, decade after decade, the neutron behaves exactly like a particle with no internal lopsidedness at all, no measurable separation between positive and negative charge, no twist in the field. The measurements have pushed the allowed value of that dipole moment down to somewhere around 10,000 trillion times smaller than what a generic unprotected value would produce. Translate that bound back into the angle sitting inside the strong force equations, and you get a number tuned to roughly 1 part in 10 billion. Nothing in the standard model requires that. There's no symmetry standing guard over this angle, the way there's a symmetry protecting other quantities in physics from drifting to arbitrary values. As far as the equations are concerned, that angle could have landed anywhere in its full range, and nobody would have had grounds to object. Instead, it landed on a value so close to 0 that 10 billion is the smallest way anyone has found to describe how precisely it avoids being anything else. Physicists call this the strong CP problem, and it sits in an odd category compared to the other case files so far. This isn't a number that needs to avoid destroying stars or preventing atoms from forming. It's a number that, by every reasonable expectation built into the theory, should be large, should be measurable, should show up clearly in a neutron sitting in a lab. Instead, it hides, refusing to reveal any trace of the violation the equations explicitly permit. No mechanism inside the standard model forces that angle towards 0. It just is, sitting there, unexplained, which left physicists searching for something the original theory never contained. And what they proposed to explain it wasn't a fix bolted onto existing particles. It was an entirely new particle, one nobody had ever detected, invented for the sole purpose of making an angle disappear. The fix has a name most people have never heard outside of a physics lecture hall: the Peche-Quinn mechanism. And the idea behind it is stranger than the problem it's trying to solve. Instead of forcing that leftover angle to 0 by hand, or hoping some symmetry already in the standard model happens to do the job, Peche and Quinn proposed adding something new: a field spread through all of space that isn't fixed in place the way most of the constants in this case file are fixed. This field can shift, settle, roll toward whatever value makes its own internal energy as low as possible. And here's the part that matters: the value where its energy bottoms out turns out to be exactly the value that cancels the strong force's CP violating angle down to 0. Nobody had to tune this by hand. The field does the tuning on its own, dynamically, the same way a ball rolling around inside a bowl eventually settles at the lowest point without anyone calculating exactly where that point is in advance. Drop that angle in anywhere, and the field finds its way to the setting that erases it. That's the mechanism. The particle it predicts is called the axion, a ripple in this new field, and it comes with a second reputation beyond just fixing the strong CP problem. Its mass and its interactions place it as a serious dark matter candidate, a particle that could be quietly filling galaxies with invisible mass without ever showing up in the searches built for other kinds of particles. Two of physics' open cases, potentially closed by the same undiscovered object. So physicists went looking, not with one method, but several, each one built to catch a different signature the axion might leave behind if it exists. Start in Washington State, in a lab running the axion dark matter experiment, known simply as ADMX. Inside sits a resonant cavity, a sealed metal chamber tuned to an extremely precise frequency, and that cavity sits inside a magnet, generating a field roughly 8 Tesla strong, powerful enough to warp the space around it in ways that matter for exactly one reason. If dark matter axions are actually drifting through that cavity right now, that magnetic field is what gives them a chance to convert into a real detectable photon. Nothing else does the converting. Without the field, an axion could pass through the entire apparatus and leave no trace at all. With it, there's a narrow chance the axion flips into a photon that a detector can actually register. ADMX tunes its cavity like an old radio, sweeping across frequency after frequency, listening for a signal at each one, because nobody knows in advance which exact frequency corresponds to the axion's true mass. It is, by a wide margin, the most sensitive axion search ever built, sensitive enough to have already ruled out entire mass ranges where a QCD axion simply is not hiding. That's real progress, even without a detection. Every ruled-out range is a piece of the map crossed off. Move to CERN, where a different approach points not into a magnet's core but straight at the sun. The CERN Axion Solar Telescope CAST repurposed a decommissioned magnet originally built for the Large Hadron Collider and aimed it at sunlight, betting that the sun's core is hot and dense enough to be quietly manufacturing axions of its own, streaming them outward along with every other form of radiation the sun produces. If those axions exist and happen to pass through CAST's magnetic field on their way past Earth, the same conversion trick applies, axion into photon, this time in the X-ray range where CAST's detectors are built to look. Years of pointing that magnet at the sun as it rises and sets have turned up nothing confirmed. But they've placed real constraints on how strongly an axion could possibly interact with light, narrowing the search from a different angle than ADMX manages. The next generation of that same idea is already being designed, a successor called the International Axion Observatory, IAXO, built to be roughly 100 times more sensitive than CAST. It doesn't exist yet, not fully. It's still in the planning and construction stages, but the design calls for a purpose-built magnet, far larger than anything repurposed from a collider aimed at the sun for years at a stretch, hunting in exactly the range CAST could only partially explore. Then there's a stranger approach entirely, one that doesn't need the sun or a dark matter halo at all. Light shining through walls experiments take a laser, fire it directly at a solid wall, and rely on a magnetic field positioned on the near side to occasionally convert a fraction of those photons into axions before they ever hit the barrier. An axion, unlike a photon, doesn't care that there's a wall in the way. It passes straight through, and on the far side a second magnetic field gives it the chance to convert back into an ordinary photon one that a detector can catch, even though as far as the wall is concerned, nothing should have gotten through at all. No axion has ever shown up on the other side of one of these walls, but the setup itself is a direct, almost theatrical demonstration of what physicists are actually betting exists, a particle that can walk through solid matter, because it barely interacts with anything at all. Decades of this, multiple experiments, multiple techniques, results checked and rechecked. Nothing yet. No confirmed detection, no signal that's held up under scrutiny. But here's the honest part of this case file. Nothing has ruled the axion out either. ADMX, CAST, and the light shining through walls experiments have each closed off their own slice of the possible mass and coupling range, and IAXO is built specifically to close off more. The search has narrowed year by year, but a real window remains open, wide enough that the QCD axion could still be sitting inside it right now, quietly making up the dark matter, filling every galaxy, waiting on the one experiment sensitive enough to finally catch it. Which leaves physics in a strange position. A number that should be free to sit anywhere between 0 and a full circle instead sits at 0 with no explanation the standard model can offer on its own. The proposed fix isn't a correction to existing equations. It's an entirely new, undetected particle, Invented because a force in nature is behaving exactly as well as it possibly could, and nobody can say why. Every case file so far has been about a number sitting in the wrong place. This one starts with something that shouldn't exist at all. Run the Big Bang forward the way the equations say it should run. Whatever process created matter in that first instant should have created an exactly equal amount of antimatter alongside it. Every particle paired with its mirror opposite, same mass, opposite charge, produced in identical quantities because nothing in the underlying physics favors one over the other. That's not a guess. That's what symmetry demands. And matter, sitting next to its antimatter twin, doesn't coexist peacefully. The two annihilate on contact, converting entirely into pure energy, into light. Run that process to completion across the whole universe, and you get a universe that never has a chance to become anything. No protons left over to build a nucleus. No electrons left over to orbit one. Just an expanding bath of photons, smooth and empty, forever. That is not the universe you're sitting in. Here's what actually happened, as best physics can measure it. For every billion pairs of matter and antimatter that existed in that first instant, one extra particle of matter came out on the other side without a partner to annihilate against.
1 out of a billion.
That leftover sliver, that billionth fraction that didn't get erased, is the only reason there's anything left over at all. Every proton in every star, every atom in every planet, every particle making up your own body traces back to that one surviving particle in a billion. Nothing else made it through. The rest went up in light billions of years ago, and has been thinning out across the universe ever since. Sit with how strange that actually is, because it's tempting to hear one extra particle in a billion and think of it as a small, forgivable rounding error, practically nothing. It isn't nothing. It's the entire reason matter exists in any form, and nothing in the basic setup of the Big Bang required that leftover to be there. Perfect symmetry was the default expectation. A universe that annihilates itself completely was the outcome physics actually predicted before anyone looked closely at what survived. The imbalance we're built from isn't a natural consequence of starting conditions. It's an exception to them, one that needed something extra to happen, some process actively tilting the scales in matter's favor during that first fraction of a second. Physics doesn't get to just note that the tilt happened and move on. If a mechanism produced that lopsided 1 in a billion survival rate, that mechanism has to satisfy some very specific requirements, because not just any kind of physical process could have pulled this off. Back in 1967, a Soviet physicist named Andrei Sakharov worked out exactly what those requirements had to be, laying down 3 separate conditions that any successful explanation would need to meet simultaneously. Not 1 or 2, all 3, together in the same moment of cosmic history. Think of it as the detective's checklist for how an alibi like this could ever hold up. 3 boxes, all needing a checkmark, before physics can even start pointing at a specific culprit. And what makes this case file worth opening isn't just that the checklist exists. It's what happens when you go looking for a suspect that actually satisfies every item on it. Box 1 on Sakharov's checklist. Whatever process tilted the scale toward matter has to actually be capable of changing the total count of baryons in existence. Protons, neutrons, and everything built from the same class of particles. Physics calls these baryons collectively, and under normal circumstances, the number of them is locked. Nothing converts a baryon into something that isn't a baryon. But normal circumstances aren't what the early universe was running on. At extreme temperatures high enough that the electroweak force hadn't even settled into its familiar form, yet physics allows for a process called a sphaleron, a kind of transition that can shift baryon number and lepton number together, breaking the usual bookkeeping rules just enough to let a mismatch start forming. It's not a violation dreamed up to patch the problem after the fact. Sphaleron processes fall directly out of the Standard Model's own equations, active and available in exactly the era when this imbalance needed to happen. Box 2. Matter and antimatter have to be treated differently by the underlying physics, not just statistically, but built into the laws themselves. This is the same C and CP violation that showed up as a mystery in the strong force, except here the direction flips. The strong force stays suspiciously symmetric when it doesn't have to. The weak force actually breaks that symmetry, and physicists have measured it directly. In decaying kaons, in decaying B mesons, confirmed data going back decades. So box 2 gets checked. The standard model does violate CP. The problem is how much. Run the actual measured strength of that violation through the math and calculate how large a matter-antimatter imbalance it could produce. And the number that comes out is nowhere close to one extra particle in a billion. It's dramatically smaller, off by many orders of magnitude from what the observed universe actually needed. Box 3. The whole process has to happen while the universe is out of thermal equilibrium, because in a system sitting calmly at equilibrium, any imbalance created in one direction gets cancelled by the reverse process running just as efficiently. You need something disruptive, a rapid transition, a moment where the universe changes state quickly enough that the forward and backward reactions can't stay in lockstep with each other. The classic version of this idea leaned on the electroweak phase transition, the moment the Higgs field settled into the value that gives particles their mass imagined as a violent, bubbling first-order transition, sharp enough to knock the system out of balance. That version needed the Higgs to behave a certain way to make the transition abrupt enough. Then the Higgs got measured. Its actual mass, the same 125 confirmed back in the second case file, puts that transition solidly in smooth crossover territory, not the sharp, bubbling break the simplest models required. The easiest version of condition 3, the one built directly into the standard model with no additions, doesn't hold up against the particle physics we've since confirmed. So here's where the checklist actually lands. Baryon number violation, present. C and CP violation, present, but far too weak. Departure from equilibrium, present in form, but ruled out in the specific mechanism that would have made it work. 3 boxes, technically checked, and yet the math refuses to add up to anything close to the imbalance sitting in front of us. The standard model satisfies Sakharov's conditions in shape, and fails them completely in magnitude. Which means whatever actually wrote this answer isn't fully contained in the physics we already have confirmed. Something beyond the standard model has to be doing heavier lifting than C and CP violation alone can manage, and one of the most promising places to go looking for it isn't among the particles already discovered. It's among the ones still hiding in a sector of physics that's barely been tested at all. That barely tested sector is neutrinos, and here's why they've become the leading suspect. Neutrinos are strange even by the standards of particle physics. They barely interact with anything. They pass through entire planets without slowing down, and for decades physicists assumed they had no mass at all. Then oscillation experiments proved otherwise, catching neutrinos switching identity mid-flight, morphing from one type into another as they travel, a behavior that's only possible if they carry mass in the first place. That discovery alone rewrote part of the standard model. But it also opened a door, because a particle that behaves this strangely, this far outside the pattern, set by every other particle physics understands, is exactly the kind of place where new physics tends to hide. The leading theory built on this is called leptogenesis, and the idea runs parallel to the baryon story but starts one level removed from it. Instead of baryons getting tilted directly, the theory proposes a heavier, undiscovered class of neutrinos existing only in the extreme energy conditions of the early universe. These heavy neutrinos decay, and they don't decay evenly. They favor one outcome over its mirror opposite the same kind of C and CP violation from Sakharov's checklist, except here it happens in the lepton sector instead of the baryon sector, producing a lopsided count of leptons before baryons even enter the picture. Then those same Sphaleron processes from before, the ones that can shift baryon and lepton number together, step in and convert part of that lepton imbalance into the baryon imbalance we actually observe. Leptons tilt first. Baryons inherit the tilt. It's an elegant chain, and it fits the hints already sitting in neutrino oscillation data. Hints that these particles carry more asymmetry between matter and antimatter behavior than anything in the quark sector ever managed. That's precisely why neutrinos look like such a natural place to search in the first place. Here's the honest state of that search right now. The hints are real, and they're coming from actual machines pointed at actual detectors, not from theory alone. Start in Japan with an experiment called T2K, short for Tokai to Kamioka. The setup fires a beam of neutrinos from a particle accelerator on the east coast of Japan, sends it straight through 295 kilometers of solid Earth, no tunnel required, because neutrinos barely notice, rock is even there, and catches what's left of that beam at the Super Kamiokande detector, a cavern buried under a mountain, and filled with 50,000 tons of ultra-pure water. Along the way, some of those neutrinos change identity, flipping from one type into another through the same oscillation process that proved they carry mass in the first place. T2K runs the experiment twice, once with a beam of neutrinos and once with a beam of their antimatter counterparts, and compares how often each version flips. If nature treated matter and antimatter identically, those two oscillation rates should come out the same. They haven't. T2K has picked up a difference between how neutrinos oscillate and how antineutrinos oscillate, a hint of the exact kind of asymmetry leptogenesis needs, sitting at a level of statistical confidence that's suggestive without being anywhere close to definitive. Move to the United States, where a similar experiment called NOVA runs a beam out of Fermilab outside Chicago and sends it 810 kilometers north to a detector near the Canadian border in Minnesota. NOVA is chasing the same oscillation pattern from a different beam energy and a different baseline distance, and comparing its results against T2K matters more than either result alone, because two independent experiments pointing in the same direction carry more weight than one experiment pointing anywhere by itself. NOVA's data leans broadly consistent with what T2K found, though the two experiments haven't lined up on every detail yet, and reconciling exactly where they agree and where they still diverge is its own ongoing piece of the puzzle. Neither experiment is built to settle this on its own. That job belongs to what's coming next. DUNE, the deep underground neutrino experiment, is under construction right now, and it dwarfs both of its predecessors. The beam starts at Fermilab, same as NOVA, but this time it travels 1,300 kilometers to the Sanford Underground Research Facility in South Dakota, a detector complex sitting nearly a mile beneath the surface in a former gold mine. DUNE is being built specifically to measure CP violation in neutrinos, with a precision neither T2K nor NOVA can reach, using detectors filled with liquid argon instead of water, a technology that lets physicists reconstruct particle tracks in far sharper detail. If the asymmetry T2K has hinted at is real, DUNE is designed to confirm it outright instead of merely suggesting it. Japan is building its own answer in parallel. Hyper Kamiokande, the direct successor to Super Kamiokande, is under construction as a water Cherenkov detector, on a scale that makes its predecessor look modest, roughly 8 times the instrumented volume, built to catch far more neutrino interactions than the current generation of detectors can manage. Paired with an upgraded beam, Hyper Kamiokande is aimed at the same question DUNE is chasing from the opposite side of the planet, and having two independent experiments hunting the same signal with different technologies is exactly the kind of redundancy physics leans on before it's willing to call something confirmed. So the hint is real, and it's being chased by some of the largest instruments physics has ever built. But here's the part that keeps this case file from closing even in the best case scenario. Everything T2K, NOVA, DUNE, and Hyper Kamiokande can measure involves neutrinos already known to exist. The light, ordinary neutrinos passing through the Earth by the trillions every second without leaving a trace. Leptogenesis doesn't run on those. It runs on a heavier, undiscovered class of neutrino, one that would have existed only in the extreme energy conditions of the early universe, decaying unevenly in a way that tilts the lepton count before sphalerons convert part of that tilt into the baryon asymmetry actually observed. Those heavy neutrinos sit at energy scales so far beyond anything a collider on Earth could ever reach directly, that no experiment currently running or currently being built has any real chance of producing one. This isn't a case where physicists are closing in on catching the culprit in the act. It's a case where the theory fits the shape of the crime perfectly, where the oscillation experiments are confirming the kind of asymmetry the mechanism needs, and where the actual suspect, the heavy neutrino doing the decaying, may simply be permanently out of reach of direct detection. Meanwhile, a different result landed recently, and it's worth naming honestly for what it is and isn't. The LHCb experiment at CERN detected CP violation in baryons directly, protons and neutrons and their heavier relatives, for the first time ever measured in that class of particle rather than in the lighter mesons physicists had studied for decades. It's a genuine discovery, confirmed real. It is also, by every calculation done on it so far too small to explain the imbalance the universe actually needed. Another confirmed data point, not a solution. So this is where the case sits. Physics agrees the imbalance is real, agrees on the checklist any explanation has to satisfy, and still cannot point to the specific mechanism that actually wrote the answer into the early universe. The leftover billionth built everything you can see, and nobody has caught the process responsible in the act. New suspect. This one isn't hiding inside a particle or a force. It's hiding in the basic shape of space itself. Physics measures something called the density of the universe, how much matter and energy is packed into it, and compares that to a specific number called the critical density, the exact amount needed to make space geometrically flat. Not flat, like a tabletop. Flat in the sense that parallel lines stay parallel forever, that a triangle's angles add up to exactly what you learned in school. That space doesn't curve back on itself in any direction. Measure the density of the actual universe, and it sits within a hair of that critical value. Not roughly close, within a fraction of a percent. Here's why that should worry you instead of comforting you. Picture two other versions of the universe, ones with slightly more or slightly less density than the exact flat value. Imagine a valley surrounded by mountains, except the valley floor represents that critical density, and any deviation from it means starting somewhere on the slope instead of the flat ground at the bottom. A universe with a little too much density is a ball rolling toward the mountain on one side, gathering speed as gravity pulls harder and harder the further it climbs. A universe with too little density is a ball rolling down the opposite slope, picking up speed as it heads away from the valley in the other direction. Neither of these situations gets more stable over time. They get worse. The deviation doesn't stay the size it started at. It compounds, snowballing further from flat with every second that passes. That's the actual danger sitting inside this case file. A universe that starts even slightly denser than critical should have curved in on itself and collapsed back down long before now, gravity winning decisively, space folding shut in a fraction of the time it took stars to even form. A universe that starts even slightly less dense should have thinned out into total emptiness, just as fast expansion running away unchecked. Matter spreads so thin that gravity never gets the chance to pull anything into a star or a galaxy at all. Both outcomes are self-reinforcing. Once you drift from flat, you don't drift back. You accelerate away from it. So for the universe to still look this close to flat after 8 billion years of expansion, the starting density in the earliest fractions of a second couldn't have been merely close to critical. It had to be tuned to a level of precision that makes the fine-tuning in every previous case file look almost casual by comparison. Physicists have run the numbers on how tight that early window needed to be, and the results describe a level of tuning that isn't measured in percentages or even fractions of a percent. It's the kind of number you'd get if you tried to balance a pencil upright on its tip and needed it to stay balanced untouched for the entire span of recorded human history and beyond, without a single outside force nudging it off course. That's the closest a physical picture gets to matching the actual precision required at the start of the universe for it to still look this flat today. Physics does have a mainstream answer for how that kind of precision could have happened without anyone tuning anything by hand. It involves the universe stretching by an almost unimaginable factor in a fraction of a second, smoothing out any curvature the way stretching a wrinkled sheet flat removes every fold. That answer has its own name, its own decades of development, and, as you're about to see, its own uncomfortable questions about whether it actually solves this problem or just moves it somewhere else. The mainstream answer is called inflation, and here's the basic idea. In the first sliver of a second after the Big Bang, space itself went through a burst of expansion, so violent it doesn't behave like ordinary cosmic growth. Ordinary expansion is gradual, a steady stretching that adds up over billions of years. Inflation is different. It's exponential, meaning the universe doesn't just get bigger. It doubles, then again, over and over in a time frame too short to properly picture, until a region smaller than an atom gets blown up to a size larger than anything that would eventually become the observable universe. Here's why that burst solves the flatness problem specifically. Any curvature sitting in space before inflation started Any deviation from flat gets stretched along with everything else. Stretch something curved by that many factors of 2 in a row, and whatever bend it had becomes undetectable. Flattened out the same way a wrinkled sheet loses its creases if you pull it taut enough. It doesn't matter how curved the universe was to begin with. After enough doublings, it looks flat, to a precision far beyond anything you'd need to explain what's actually observed today. This is why inflation became the standard answer, instead of just one option among several. It doesn't only fix flatness. The same burst of expansion explains why regions of the universe so far apart that light could never have traveled between them still show almost identical temperatures. A separate puzzle physicists call the horizon problem. One mechanism, two major mysteries solved by the same stretch of exponential growth. That kind of efficiency is exactly what makes a theory attractive in physics, and it's a large part of why inflation sits at the center of the standard cosmological model instead of on its margins. But here's where the case file gets uncomfortable again, because inflation doesn't arrive for free. To actually happen, the theory needs something driving that expansion, a field, usually called the inflaton, sitting in a very particular starting configuration with a very particular shape to its potential energy. The field has to start high enough up its energy curve to sustain the stretch, and the curve itself has to be shaped just right, flat enough in the right places to let inflation run long enough to solve the flatness and horizon problems, but not so flat that it never stops, and structure never gets the chance to form afterward. None of that comes pre-specified by any deeper theory. It has to be arranged, tuned by hand in the models that produce it, in order for inflation to do the job it's credited with doing. Critics inside physics have pointed at this directly. You don't remove fine-tuning by inventing a mechanism that itself requires fine-tuning to work. At best, the argument goes, you've relocated the problem from the density of the early universe to the shape of a field nobody has detected and a potential nobody has derived from first principles. Defenders of inflation don't deny the field needs specific conditions to work. They argue those conditions are far less severe than the flatness problem they're solving, a trade worth making even if it isn't perfectly clean. That argument hasn't settled. It's still being published on, still being modeled, still splitting serious physicists into camps, which leaves this case file sitting in an odd place. The best answer physics has for one fine-tuning problem stands accused by physicists working inside the same field of being a fine-tuning problem itself. Step back from the case files for a moment and look at what's actually sitting on the table. 5 separate numbers. 5 completely different branches of physics. Dark energy comes out of general relativity and cosmology. The Higgs mass comes out of particle physics and quantum field theory. The strong force comes out of nuclear physics. The matter-antimatter ratio comes out of particle decay and the physics of the early universe. The flatness of space comes out of geometry, applied to the largest scales anyone has ever measured. These aren't 5 versions of the same problem wearing different costumes. They're 5 different problems, solved with 5 different sets of tools, by scientists working in 5 different corners of the field. And every single one of them lands in the same place. A range so narrow that nudging the number even slightly erases the possibility of atoms, stars, galaxies, or anything resembling structure at all. Here's the detail that should sit with you longer than any individual case file did on its own. Nobody went looking for this pattern. Einstein wasn't thinking about the strong nuclear force when he crossed out his cosmological constant in the 1920s. Sakharov wasn't thinking about the Higgs boson when he wrote down his 3 conditions in 1967. The physicists measuring the neutron's electric dipole moment decade after decade weren't cross-referencing their results against the flatness of space. These mysteries were uncovered independently, separated by years, and sometimes by entire careers, by people solving the specific problems sitting in front of them, with no reason to suspect their answer would end up sitting in the same uncomfortable neighborhood as 4 other unrelated answers. Name the pattern plainly without dressing it up further. Dark energy, the Higgs mass, the strong nuclear force, the leftover matter from the early universe, and the geometry of space itself. All 5 sit tuned right at the edge of what allows anything to exist beyond a formless spread of particles and light. Move any one of them, and the case file closes itself, because there's no one left to open it. Which leaves exactly one question worth asking, and it's the question this entire investigation has been building toward without naming it directly until now. Is this a coincidence? 5 unrelated dials that all happen to land in a survivable position by chance. Is there a hidden mechanism, some deeper layer of physics not yet discovered, quietly forcing each of these numbers to its observed value for reasons still unknown? Or is this something else entirely, a question that physics itself may not be built to answer from the inside? That question split the field into two camps, and neither one is comfortable. The first camp doesn't try to explain why any single number sits where it sits. It changes the question entirely. Here's the core move. Suppose there isn't just one universe. Suppose there are enormous numbers of them, each one a separate region with its own values for dark energy, its own Higgs mass, its own strength of the strong force, its own leftover fraction of matter, its own geometry. Most of these regions are hostile. In some, dark energy rips space apart before an atom can form. In others, the strong force is weak enough that hydrogen is the only element that will ever exist. Nobody experiences those universes, not because they're forbidden, but because there's nobody there to do the experiencing. Structure never got the chance to build a single observer. Only in the rare regions where the dials happen to land in the survivable range does anyone exist to look around and ask why. This is the anthropic principle, and stated plainly like that, it isn't circular. It's closer to a filter. You don't need a reason why the numbers are survivable, because the only place anyone could ever be standing to notice them is a place where they already are. Physicists split this into two versions, and the split matters. The weak version says exactly what's been described. Out of many possible universes, observers only show up in the survivable ones, so finding ourselves in a survivable one tells you nothing except that you exist. Most working physicists who take anthropic reasoning seriously stop there. The strong version goes further, arguing the universe was somehow required to produce observers, which edges toward a claim about purpose that most of the field treats as philosophy dressed up as physics rather than a testable idea. The weak version is the one doing any real work in this debate. For the weak version to mean anything, though, you need an actual mechanism generating those many universes in the first place, not just a hypothetical. This is where string theory enters the argument. Its equations don't settle on one unique configuration for the universe. They allow for a staggering number of possible vacuum states, each with its own version of the physical constants, an estimate that lands somewhere around 10 raised to the 500th power. That's not a typo repeated for effect. It's a number large enough that writing out every zero would take more space than this entire investigation has used so far. Physicists call this range of possibilities the string landscape, and if it's real, it hands the anthropic argument exactly the kind of mechanism it needs. Not a philosophical guess about many universes, but a mathematical structure that produces them as a natural consequence of the theory. Here's the honest appeal of this position, stated without dressing it up. If the landscape is real, none of the 5 case files need a deeper cause. Dark energy doesn't need a reason for its exact value beyond survivability. The Higgs mass doesn't need a hidden symmetry protecting it. The numbers just are what they are in this particular pocket of an enormous space of possibilities, and we're here because this pocket allows it. And yet, sit with the physicists who actually hold this position, and you find something unexpected: discomfort. Even among people defending the landscape, there's an admission that this feels less like solving a mystery and more like declaring the mystery permanently out of reach. Here's the problem with that discomfort. It isn't just a feeling. It points at something structurally wrong with the argument itself. A theory that produces one universe and gets it right is doing science. A theory that produces 10 to the 500th power possible universes and tells you our particular set of values is simply one option among that pile isn't making a prediction anymore. It's making room for every prediction at once. Ask what value dark energy should have, and the landscape doesn't give you an answer. It gives you a range so wide that almost any number you could have measured would have fit somewhere inside it. That's not a theory being confirmed by observation. That's a theory that can't be contradicted by observation, because there's no result it would have ruled out in advance. That's the core objection, and it's not a minor technical complaint. Physics normally works by making a claim specific enough that it could fail. You calculate a number, you go measure it, and if the measurement doesn't match, the theory is wrong. The string landscape doesn't offer that kind of exposure. Whatever we measure, there's a pocket in that 10 to the 500th power that would have contained it. Critics inside the field have said this plainly. A framework that accommodates every possible outcome isn't functioning as a scientific theory in the way general relativity or quantum mechanics function. It's functioning as a mathematical container large enough to hold whatever universe happens to show up inside it, ours included, without ever being forced to say anything falsifiable about it beforehand. Now, this camp does have one card to play, and it's a real one. Back before dark energy's actual value was pinned down by observation, physicist Steven Weinberg used anthropic reasoning to estimate roughly what that value needed to be. His argument was straightforward: push dark energy much higher than a certain threshold, and galaxies never get the chance to condense out of the early universe at all, which means no observer could ever exist to measure a larger value in the first place. Restrict the possible range to only the values compatible with galaxy formation, and Weinberg's estimate landed in the same rough neighborhood as the number astronomers actually measured years later. That's a genuine anthropic prediction, made ahead of the data, that turned out to be roughly correct. But one correct estimate, built on a fairly generous margin, isn't the same as explaining a number to the precision this case file actually demands. Skeptics point out that Weinberg's success narrowed things down to an order of magnitude, not to the exact figure sitting at the center of the vacuum catastrophe. It's a hint that anthropic reasoning has some predictive teeth. It is nowhere close to settling the argument for anyone who wanted a mechanism instead of a filter. Which is exactly why an entirely different camp of physicists looked at all of this, the landscape, the filter, the one partial success story, and decided none of it was good enough. They didn't want a reason the numbers were survivable. They wanted a reason the numbers were what they are. And that search has been running in parallel this whole time. That other camp starts from a simple refusal. They won't accept the anthropic answer, not because it's logically broken, but because of what it does the moment you accept it. It ends the search. Say the numbers are what they are because we couldn't exist to see them otherwise, and there's nothing left to calculate. No equation to solve. No experiment worth running. The mystery doesn't get resolved. It gets closed, filed away as a fact of our particular address in a landscape too large to interrogate further. For a certain kind of physicist, that's not an answer. That's the moment you stop doing physics. So this camp went looking for something the landscape refuses to offer, an actual mechanism, something that forces these numbers to their observed values the way a law of physics forces anything, rather than something that merely permits them because nothing else survived. You've already met their candidates in earlier case files, and it's worth naming plainly what they were actually trying to do. Supersymmetry wasn't just a hunt for exotic particles. It was an attempt to explain why the Higgs mass sits where it sits, using a symmetry that would cancel the runaway quantum corrections instead of leaving them unexplained. Technicolor and composite Higgs models made the same attempt from a different angle, trying to derive the electroweak scale from new strong dynamics rather than accept it as an unprotected coincidence. Even modified gravity, raised earlier around the flatness and expansion questions, belongs in this same family of effort, a proposal that the numbers we measure are downstream of a deeper rule, not the product of a cosmic lottery. Here's the honest accounting. None of it has worked. Supersymmetry predicted partners at a scale the Large Hadron Collider should have reached, and found nothing. Technicolor and composite Higgs models have been squeezed hard by precision measurements that keep confirming the Higgs behaves almost exactly like the simplest version of the theory, leaving less and less room for the strong new dynamics these models require. Modified gravity solves pieces of the puzzle while struggling to match the full range of data that the standard model, cracks and all, still accounts for. Every attempt at a deeper mechanism carries its own unresolved failure sitting right next to its ambition. So the standoff sits exactly here, unresolved on both sides. One camp says the universe doesn't owe anyone a reason that a filter is a complete explanation. Once you understand what a filter actually does, and that demanding something more is asking physics to answer a question it was never built to answer. The other camp says giving up on a mechanism isn't restraint, it's surrender, and that every other advance in physics came from refusing to accept that's just how it is as a final word. Quantum mechanics didn't stop at behavior nobody could explain. Neither did the structure of the atom.
Why should these 5 numbers be the place physics finally stops asking why?
Neither side is winning this argument. and neither side is losing it either. There's no scheduled resolution, no experiment on the calendar that both camps agree would settle it. Papers keep getting published on both sides of this divide. New landscape calculations alongside new supersymmetry variants, new anthropic arguments alongside new attempts at derivation. The case file stays open, not because nobody's working it, but because the two teams working it can't agree on what would even count as closing it. While that standoff sits unresolved, a completely separate crack opened up in the foundation underneath it. Not a philosophical disagreement this time. A measurement problem? Two different teams, both careful, both trusted, pointed their instruments at the same number and came back with two different answers. The number is the Hubble constant, and it tells you how fast the universe is expanding right now. One team, led by astronomer Adam Rees and known by the acronym SH0ES, built their answer from the ground up, starting with stars close enough to measure directly and working outwards step by step until they reached galaxies billions of light years away. The other side didn't look at individual stars at all. They looked at the Planck satellite's map of the cosmic microwave background, the ancient light released when the universe was only a few 100,000 years old, and ran that data through the standard cosmological model to calculate what today's expansion rate should be if the early universe evolved the way the equations say it should. Rees's team came back with 73 kilometers per second per megaparsec. The Planck team came back with 67. Those two numbers should be the same number. They're measuring the same universe, the same expansion, the same moment in cosmic history. They aren't the same number, and the gap between them isn't hiding inside the error bars anymore. It's sitting at 5 sigma, the same statistical bar physics uses before it will even call something a confirmed discovery. 5 sigma means the odds of this gap showing up by chance, if the two methods were actually measuring one true value, land somewhere around 1 in 3 million. Physics doesn't shrug off odds like that. It goes looking for what's broken. Here's how the local number actually gets built, because the chain matters. It starts with parallax, the oldest trick in astronomy, measuring how much a nearby star appears to shift position as Earth orbits the Sun, and using that shift to calculate distance directly, with nothing borrowed from any cosmological model. The Gaia satellite has measured parallax distances to enormous numbers of stars, with a precision no ground-based instrument could match. Those precise distances calibrate Cepheid variable stars, a class of star that pulses in brightness at a rate directly tied to how luminous it actually is. Once you know exactly how bright a Cepheid really is, you can find one sitting inside a more distant galaxy, compare its true brightness to how dim it looks from here, and calculate that galaxy's distance directly. That's rung 2. Rung 3 takes those newly calibrated galaxies and uses them to calibrate type Ia supernovae, the exploding stars that detonate at almost exactly the same brightness every time, because they all reach the same mass threshold before igniting. Once a supernova is calibrated this way, it becomes a distance marker usable out to galaxies far beyond where individual Cepheids can even be picked out. Stack those 3 rungs together, parallax anchoring Cepheids, Cepheids anchoring supernovae, and you've built a ladder reaching from stars in our own galactic backyard out to galaxies billions of light years away, each rung checked directly against the one underneath it. That's the method that produces 73. It doesn't borrow a single assumption from the standard cosmological model. It's built entirely from direct measurement, one calibration at a time, all the way up the ladder. Here's the part that should trouble you more than the gap itself. Physicists assumed reasonably that this was a problem better instruments would eventually fix. If the ladder had a subtle flaw hiding somewhere, more precise parallax data would expose it. If the cosmic microwave background analysis had missed something, a sharper map would correct it. That's how most disagreements in physics get resolved. Better data closing the distance until one side turns out to have been slightly wrong. The opposite happened here. Gaia's parallax measurements got better. The supernova samples got larger. The Planck data got reanalyzed and reprocessed by multiple independent teams using different techniques. Every one of those improvements should have narrowed the 9% gap if it were hiding a fixable error. Instead, the gap held its ground, and in some analyses, it widened slightly. Physicists gave the standoff a name, the Hubble tension, And a disagreement doesn't earn a name like that unless it has refused to close for long enough that the field needs a shorthand for talking about it. Follow the higher number forward, and the trouble compounds instead of settling. A faster expansion rate today means less time has passed, since everything sat compressed into a single point, which means a younger universe than the cosmic microwave background side of the calculation implies. Run the math on 73, and the universe comes out younger than the 13. 8 billion years the Planck data supports. Now hold that against the oldest stars astronomers can actually see, the ones sitting in globular clusters, dated independently through stellar physics, that has nothing to do with cosmic expansion at all. Those stars come out close to 13 billion years old on their own. Push the universe younger to match the higher Hubble number, and you land in a universe holding stars older than the universe itself. That isn't a subtle tension anymore. That's two separate branches of physics contradicting each other directly, and nobody has found the error yet. This isn't a separate mystery running alongside the 5 case files you've already walked through. It's a crack in the same structure holding all 5 of them up. Every constant in this investigation, every narrow surviving range, every fine-tuned number gets measured and interpreted through the same cosmological model that's currently failing to agree with itself on something as basic as how fast space is expanding today. If the foundation is already showing daylight through it, the question becomes whether that crack reaches all the way down to the numbers this whole case file has been built around. Here's what a 9% disagreement actually does once you stop treating it as an isolated measurement dispute and start treating it as an input. Every fine-tuned number in this investigation didn't arrive standalone. It arrived wrapped inside a model, and that model depends on knowing the expansion rate with confidence. If the expansion rate itself carries this much uncertainty, that uncertainty doesn't stay contained to one number on one chart. It runs downhill into everything built on top of it, including the successful framework physicists point to when they explain why dark energy or the flatness of space landed where they did. And it gets worse once you follow the math forward instead of just noting the disagreement exists. A faster local expansion rate implies less time has passed since the Big Bang than the slower rate would suggest. Run the higher of the two Hubble numbers through the standard equations, and you get a universe that's younger than the one built from the cosmic microwave background side of the measurement. That's not a comfortable rounding difference. Astronomers have independently dated some of the oldest stars in globular cluster stars, whose age comes from a completely separate branch of physics, stellar evolution rather than cosmic expansion. And those stars come out looking close to the age of the universe under the slower expansion estimate. Push the universe younger to match the faster number, and you land in the position of stars appearing older than the cosmos that supposedly formed them. That is not a mystery sitting outside the standard model, waiting patiently to be explained by some future discovery. That's a contradiction sitting inside the model as it currently stands. One number implying an age too young for objects the model itself says already exist. A structure can carry an unexplained gap and still function. A structure can't carry an internal contradiction and claim to be finished. Now connect this directly back to the first case file, because the implication doesn't stop at age. The reason physicists have spent decades treating the cosmological constant as fixed is that it's easier to work with a single unchanging number. But if dark energy hasn't been constant across cosmic history, if it behaved differently 5 billion years ago than it does today, then the number sitting at the center of the vacuum catastrophe isn't a fixed target at all. It's a present-day snapshot of something that may have been moving the entire time. Tuning an argument around a fixed value only makes sense if the value stayed fixed long enough to matter. A shifting dark energy breaks that assumption at the root. So the fine-tuning case was never resting purely on the values themselves. It was resting just as much on the model those values live inside. And that model is currently disagreeing with itself over something as fundamental as how old everything is. The numbers might still be exactly as narrow as this investigation has described, but the ground underneath the numbers has a crack running through it, and that crack reaches further than anyone expected when it was first discovered. Here's a fact that gets stranger the longer you sit with it. In 2013, 3 astronomers went looking for nothing in particular and found a hole in space instead. Ryan Keenan, Amy Barger, and Lennox Cowie sat down with a survey of more than 35,000 galaxies, mapping out their positions and distances across billions of light years in every direction from Earth. The kind of methodical counting exercise that sounds almost administrative until you see what the count actually turned up. Everywhere they looked, out to roughly a billion light years, there were fewer galaxies than there should have been. Not a small shortfall. Something close to 20% less matter than the cosmic average, stretched out into a sphere with our own galaxy sitting almost dead center of it. They checked the number against multiple independent surveys, ran it through different wavelength bands, sliced the data different ways to see if the deficit was an artifact of how one particular telescope saw the sky. It held every time. Scientists gave it a name built from the initials of the three researchers who found it, the KBC void. And once you understand what that number actually means, the name feels far too casual for what it's describing. A 20% deficit spread across a billion light-year sphere isn't the kind of gap you'd expect from ordinary cosmic clumping. The normal unevenness of galaxies clustering here and thinning out there. Run the standard model forward in simulation after simulation. Generate universe after universe the way the equations predict matter should settle, and avoid this large, this empty, this centered on any one random point almost never shows up. Some researchers who ran the statistics on exactly how rare this is came back with a figure of 10 sigma. Put that number in context. 5 sigma is the bar physics uses before it will call something a confirmed discovery. Odds of roughly 1 in 3 million that you're looking at a fluke. 10 sigma isn't just twice as strict. It's a deviation so severe that you would not expect to find one region like this anywhere in the entire observable universe by chance. Not in one sample, not in 1,000 samples. And yet here we are, sitting inside it, the void wrapped around us in every direction we can measure. That statistical strangeness would be an interesting footnote on its own. It becomes something else once you connect it to a problem already sitting on the table. Living inside an underdense region doesn't just mean fewer galaxies overhead. It changes what you measure when you point a telescope outward and calculate how fast everything is moving away from you. Matter outside the void, in the denser regions surrounding it, pulls gravitationally on everything inside it, including us, adding an extra outward push to galaxies caught in that gravitational tug-of-war. That extra push shows up as an inflated local expansion rate, faster than the true cosmic average, measured from right where we happen to be standing. This isn't a theoretical effect sitting only in the math. The Milky Way itself is moving right now at roughly 600,000 miles an hour relative to the void's center, driven by exactly this imbalance. That's not cosmic expansion carrying us along passively. That's a real, measurable velocity. Our galaxy and everything gravitationally bound to it getting physically pulled outward, away from the underdense region and toward the denser walls of galaxies surrounding it. Gravity from the matter outside the void is winning a tug-of-war against the near absence of matter inside it, and the Milky Way is caught in the middle of that pull, accelerating away from a center. It can never fully escape because the void itself keeps growing right along with us. Which means the Hubble tension you just walked through, the 9% gap between the early universe measurement and the local distance ladder measurement, might not be two competing truths at all. It might be one true cosmic average and one local number, quietly distorted by the accident of where we're located. Some physicists now argue this void alone could account for part of that gap, maybe even all of it, without requiring a single new particle, a revised law of gravity, or a fundamental rewrite of the standard cosmological model. Just geography, doing what geography does to a measurement taken from inside a hole instead of from a representative patch of space. Every supernova we use to calibrate the local expansion rate sits inside this same underdense bubble riding the same outward push, which means the distance ladder built from those supernovae may be measuring our neighborhood's peculiar motion and mistaking it for the universe's true expansion rate. But sit with what that means for a principle physics has leaned on since Copernicus first knocked Earth out of the center of everything. Cosmology runs on something called the Copernican principle, the assumption that no location in the universe is special, that averaged over large enough scales, any patch of space looks statistically like any other patch. That Earth's position is unremarkable in every sense that matters. Science has spent 5 centuries stripping away one privileged position after another. Earth wasn't the center of the solar system. The sun wasn't the center of the galaxy. The galaxy wasn't the center of anything. Each correction pushed humanity further from the middle of the picture, and cosmology's entire mathematical framework assumes that trend has nowhere left to go, that at the very largest scales, uniformity finally wins and no observer anywhere gets a special seat. A 10 sigma void with us sitting near its middle doesn't just bend that assumption, it breaks it outright. Either we drew an almost impossibly unlikely position in an otherwise uniform universe, or the uniformity itself was never as solid as the models required it to be, and physics still hasn't agreed on which of those two uncomfortable options it prefers. So here's where the case file needs to be honest with itself, because it would be easy to take that void and let it swallow everything else this investigation has built. If our own location is skewing what we measure, if the ground under one number is really just an accident of geography, the tempting move is to ask whether all 5 case files dissolve the same way. They don't, and saying so isn't a concession. It's the thing that keeps this argument credible. Think about what the void can actually touch. It touches measurements that depend on distance, on light traveling to us across billions of years, on how fast galaxies appear to recede from a specific vantage point in space. That's the expansion rate. That's the Hubble tension, or at least a share of it. That's a number tied directly to where the telescope is sitting when it takes the reading. Now, hold that up against the Higgs mass. The hierarchy problem has nothing to do with what's overhead in the night sky. It comes from a comparison between two energy scales, the weak scale and the Planck scale, both of which are properties of particle physics itself, tested in colliders that don't care whether the lab sits inside an underdense region or a dense galactic cluster. Move the entire Milky Way to the densest supercluster in the observable universe, and the Higgs boson still weighs what it weighs. The mass wouldn't shift by a single decimal. The strong nuclear force works the same way. The range that lets protons and neutrons bind into stable nuclei, instead of instantly fusing or falling apart, isn't a measurement taken by looking outward. It's a property of the force itself, confirmed in laboratory experiments here on Earth, in accelerators smashing particles together at energies that have nothing to do with cosmic geography. A void 20% underdense doesn't touch it. A void twice that size wouldn't touch it either. And the matter-antimatter asymmetry sits furthest from anything the void could explain away. That leftover billionth of matter isn't a distance measurement, isn't a recession velocity, isn't anything that depends on your position in the cosmic web. It's a ratio baked into the particles filling this room right now, measured directly, with no reference to how many galaxies happen to be visible from where you're standing. So the honest accounting looks like this. The void might genuinely explain part of the Hubble tension. It might soften the case around dark energy's measured value, since that number does depend on distances and expansion rates taken from inside a possibly unusual patch of space. But 3 of the 5 case files don't bend at all. The Higgs mass, the strong force, and the matter-antimatter ratio stay exactly as tight, exactly as unexplained, regardless of whether we're sitting in a void, a supercluster, or dead center of the whole observable universe. Which sharpens the investigation rather than weakening it. Strip away the one case file that geography could plausibly touch, and you're left with mysteries that have nowhere left to hide behind our address in the cosmos. Strip away the geography, strip away the void, and you're left standing in front of the actual seam where this whole problem lives. 2 theories, both correct, both impossible to reconcile with each other. General relativity describes gravity as the shape of space and time bending around mass, and it works with extraordinary precision at the scale of planets, stars, galaxies, the entire structure of the cosmos this investigation has been walking through. Quantum mechanics describes the behavior of particles at the smallest scales anyone has ever probed. Electrons, quarks, photons, governed by rules that look nothing like smooth curving geometry. Quantum mechanics deals in probabilities, in discrete jumps, in a fog of possible outcomes that only resolves into something definite the moment you measure it. Both theories have been tested to punishing degrees of accuracy. Neither one has failed a single experiment thrown at it in its own domain. The trouble starts the moment you try to make them speak to each other. Take the rules that govern the smallest scales and try to apply them to gravity itself. Try to treat gravity the way quantum mechanics treats every other force, and the mathematics doesn't bend. It breaks. The equations spit out infinities, numbers that grow without limit, In places where a working theory is supposed to hand you something finite and measurable, physicists have spent the better part of a century trying to patch this seam, trying to build a framework where general relativity and quantum mechanics both hold simultaneously, and no attempt has produced a version confirmed by experiment. This isn't a rounding error waiting on more precise instruments. It's a structural incompatibility between the two most successful theories physics has ever built. And here's why that seam matters directly to this case file, instead of sitting off to the side as background theory. Dark energy isn't neatly filed under one theory or the other. It sits exactly where the two frameworks are supposed to meet and don't. Dark energy behaves like a property of space itself, which puts it under the jurisdiction of general relativity, the same theory that describes cosmic expansion and the large-scale geometry this investigation has already covered. But the value quantum mechanics predicts for the energy hiding inside empty space, the vacuum energy generated by particles flickering in and out of existence at the smallest scales, comes from calculations that belong entirely to quantum field theory. Ask general relativity what dark energy should look like, and you get a number small enough to allow galaxies. Ask quantum mechanics the same question, and you get a number so large it would have torn the universe apart before a single atom formed. Two branches of physics, both trusted, aimed at the same quantity, and they don't just disagree by a small margin. They disagree by the entire scale of the vacuum catastrophe this investigation opened with. That's not a coincidence of bad luck in how the calculation was done. It's the seam itself, showing up exactly where you'd expect it to, in the one number that has to answer to both theories at once, which means solving dark energy's fine-tuning, actually explaining why the number sits where it sits, instead of where either theory predicts on its own, may not be possible without solving the deeper incompatibility first. You can't fully close this case file by working on dark energy alone. You may need to fix the seam underneath it, the same seam physics has been staring at unresolved for 100 years. Before this investigation goes any further, it owes you a serious objection, one that doesn't come from outside physics, but from inside it. A number of physicists look at everything laid out so far, the vacuum catastrophe, the Higgs sitting where it shouldn't, the narrow surviving range for the strong force, and argue that the entire framing might be built on a mistake. Not a mistake in the measurements, a mistake in what we're allowed to call unlikely in the first place. Here's the objection stated plainly. Every time this case file has said something like the odds of this value occurring are 1 in 10 to some enormous power, that claim is quietly resting on an assumption most people never notice. To calculate odds, you need a spread of possible values to calculate odds against. You need to know what the full range of options was, and how likely each option was to occur within that range, before you can turn around and say the actual result was rare. Flip a coin and get heads 10 times in a row, and you can call that unlikely because you know a coin has exactly two sides, each equally probable. Nobody has that kind of clean starting point for the Higgs mass, or for dark energy, or for the strong force. Nobody knows the full menu of values these constants could have taken, or whether every value on that hypothetical menu was equally likely to come up. Without that menu, the math this whole investigation has leaned on gets shakier than it sounds when you first hear it. Saying the observed value represents a 1 in 10 to the 120 coincidence assumes you know the size and shape of the space it was drawn from. If nobody has a theory that specifies what values were actually available, the calculation isn't measuring a real probability. It's measuring how far the observed number sits from a guess about what the full range might look like, dressed up in the language of odds to make it sound more rigorous than it is. Critics call this a category error, taking a number that has no confirmed underlying distribution and treating it as though it had one. This is a fair objection, and it deserves to be treated as one rather than waved off. It doesn't mean the 5 case files evaporate. It doesn't mean dark energy stops sitting at the edge of the vacuum catastrophe, or that the Higgs mass stops requiring cancellation nobody has explained. What it does is narrow what you're allowed to claim about the mystery. You can still say these values sit in a range that permits structure and stars and atoms. You can still say physics has no mechanism explaining why. What gets harder to defend is the specific language of astronomical odds, the claim that we've calculated exactly how improbable this outcome was, when the calculation depends on an assumption about possibility space that nobody has actually confirmed. That distinction matters, and it changes how the rest of this argument needs to be built from here forward. That objection deserves an honest response, and the honest response is that it doesn't land the same way on every case file sitting on this table. Some of these arguments lean hard on probability talk, others don't need it at all. Start with the strong nuclear force, because it's the cleanest example of a fine-tuning claim that survives this kind of scrutiny without flinching. The case for a narrow surviving range there was never built on a probability distribution stretched across every conceivable strength that force could have taken. It was built on direct physical consequence. Turn the force up, and you watched protons fuse together before hydrogen ever gets the chance to exist. Turn it down, and nuclei simply don't hold no matter what value you plug in around that threshold. That's not a statement about how unlikely the observed strength is against some unconfirmed menu of alternatives. That's a statement about what happens on either side of the line, checked through physical reasoning that doesn't require knowing the full range of possibilities beforehand. You don't need a probability distribution to know a bridge collapses past a certain load. You just need to know what happens at the load. The matter-antimatter asymmetry sits on even steadier ground, because it isn't a probability claim in the first place. It's a measurement. Physicists didn't calculate the odds of one extra matter particle surviving per billion annihilated pairs and then go check whether reality matched the odds. They measured the ratio directly, confirmed it across independent methods, and then went looking for a mechanism inside the standard model that could account for it. They didn't find one. Sakharov's three conditions are satisfied in form and fail in magnitude, and that failure has nothing to do with assumptions about possible universes or probability spread. It's a number sitting in front of physicists with no explanation attached to it. Full stop. So the balanced position looks like this. The earlier objection is fair, and it does real damage to the loosest versions of this argument, the ones that lean on phrases like 1 in 10 to the 120, as though that figure were as solid as a laboratory measurement. Dark energy's fine-tuning claim takes the hardest hit here, because it depends most heavily on comparing an observed value against a theoretical prediction built from assumptions about cutoffs and possibility space that remain genuinely contested. The Higgs mass sits somewhere in the middle, resting on naturalness arguments that most of the field still finds compelling, but that aren't beyond challenge either. The strong force and the matter-antimatter ratio don't need any of that scaffolding to stay standing. They hold up under the same skepticism that weakens the other cases, because they were never resting on a probability calculation to begin with. That's the honest shape of where this argument stands, once you let the objection do its work instead of dismissing it outright. There's one more possibility this case file hasn't put on the table yet, and it doesn't try to explain dark energy's value. It questions whether that value is even a fixed thing to begin with. Every argument so far has treated the cosmological constant the way its name suggests, as a single, unchanging number stamped into the fabric of space and locked there for the life of the universe. That's the assumption behind the vacuum catastrophe, behind the dial metaphor, behind the entire framing of a number sitting frozen at one precise setting since the beginning. But a serious alternative has been building in the background of cosmology for years, one that treats dark energy not as a constant at all, but as a field, something with the capacity to shift in strength as the universe ages. Physicists call this quintessence. Instead of a fixed pressure baked into empty space forever, quintessence describes a dynamic quantity, capable of weakening or strengthening over billions of years depending on how the underlying field evolves. This isn't idle speculation with nothing behind it. In 2024, the Dark Energy Spectroscopic Instrument, a survey mounted on a telescope in Arizona and built specifically to hunt for exactly this kind of drift, released results from the largest three-dimensional map of the universe ever assembled. Over its first year of operation, it measured the positions and distances of roughly 10 million galaxies, using thousands of optical fibers to capture light from thousands of targets simultaneously, night after night. The goal wasn't just to measure how fast the universe is expanding today. It was to trace that expansion rate across 11 billion years of cosmic history, watching how dark energy has behaved at every stage along the way, rather than assuming it's held one value the entire time. Here's how physicists actually describe a number that might be moving instead of fixed. They use two parameters together, called W0 and W sub A. Naught describes dark energy's behavior right now, in the present era, And if dark energy really is Einstein's old cosmological constant, unchanging and eternal, W naught should equal exactly -1. No more, no less. W sub A is the second number, and it captures something naught can't. How much that value is shifting over cosmic time, whether dark energy is strengthening as the universe ages or weakening. A true constant would give you a flat line, W naught at -1 and W sub A at 0. No motion at all, the same fixed pressure baked into space at the beginning, and still sitting there unchanged today. That is not what the DESI data showed. The results hinted that W0 might sit slightly above -1, not below it, which matters, because below -1 would put dark energy into what physicists call phantom energy territory, the kind of runaway strengthening this investigation touched on earlier, that ends in the big rip. Instead, the hint pointed the other way. Dark energy appearing stronger roughly 5 billion years ago, then gradually losing strength as time went on, trending toward weaker rather than stronger today. Paired with a W sub A that isn't sitting at 0, the data described a universe where dark energy has a history, an actual trajectory instead of a fixed setting. Now, the honest caveat matters here as much as the finding itself. This result sits at right around 2 sigma significance. Physics does not call 2 sigma a discovery. 5 sigma is the same bar this investigation has already applied to the Hubble tension and the void, and 2 sigma falls well short of it, corresponding to roughly a 1 in 20 chance the pattern appeared by ordinary statistical noise rather than anything real. It's a hint, not a discovery, the kind of signal that needs years of additional data before anyone can call it confirmed. Plenty of interesting patterns in cosmology have shown up at this level of confidence and faded once larger datasets came in. Nobody is rewriting the textbooks on the strength of one survey, and DESI's own team has been careful to frame it that way, as a signal worth watching rather than a result worth announcing. But even sitting at that lower confidence, a hint like this changes the shape of the entire argument this investigation has been building. Every debate about whether dark energy's value is a coincidence, a filtered outcome, or a category error resting on shaky probability math has been treating that value as a single fixed target, one number that either does or doesn't require an explanation. If dark energy has actually been drifting across cosmic time, then the number physicists have spent decades trying to explain isn't the number that mattered in the early universe at all. It's just where the dial happens to sit today, mid-motion, on its way to wherever it's heading next. And that shifts the entire question this case file has been asking. Up to now, every argument about dark energy's fine-tuning has been a question about a single fixed target. Why does this one number sit at this one value instead of the enormous value quantum mechanics predicts? That's a hard enough question on its own. But a dynamic dark energy doesn't just move the target. It changes what kind of question you're even allowed to ask. You're no longer asking why a number was frozen into place at the beginning of the universe. You're asking why a field exists at all, why it started at whatever value it started at, why it's moving in the specific direction the DESI data hints at rather than some other direction, and what determines the shape of its future path. Explaining a frozen constant and explaining a moving field are not the same problem wearing different clothes. They're different problems entirely, and the second one is arguably harder because now you need a mechanism for the motion itself, not just a mechanism for a single value. The fine-tuning case was never just resting on values. As you've now seen twice over, it also rests on a model that keeps showing you it isn't finished changing shape underneath your feet. That drift matters for more than just how physicists argue about the past. It decides the future too, because dark energy doesn't just explain why the universe looks the way it does right now. It picks the ending. Physics currently has 3 candidate endings on the table, and which one happens comes down entirely to what dark energy does next. The first is called the Big Freeze, and current data makes it the frontrunner. Dark energy holds roughly steady. The universe keeps expanding at something close to its current pace, and galaxies drift farther and farther apart until the space between them grows too vast for light to bridge. Picture it stretched across real time instead of a single sentence. 100 billion years from now, star formation has mostly stopped, because the gas clouds that used to collapse into new stars have been pulled too thin and too far apart for gravity to gather them anymore. A trillion years in the last of the small, slow-burning red dwarf stars, the ones that can sip their fuel for eons longer than anything like the sun, finally go dark one by one, and no new light replaces them anywhere. What's left isn't stars. It's corpses, white dwarfs cooling into cold spheres of crystallized carbon. Neutron stars sitting silent and dense. Black holes, patient and enormous, doing the only thing left to do, which is slowly evaporating. That evaporation runs through a process called Hawking radiation, where a black hole leaks particles at the edge of its event horizon, so gradually that even the largest black holes known today would need a number with more than 60 zeros in it measured in years to fully boil away into nothing. No dramatic flash marks that ending either, just less and less, stretched across a timescale so long that trillions of years starts to look like a rounding error. Eventually, there's nothing left but a thin, cold spray of particles and radiation, spread through an infinite volume of expanding space, sitting at a temperature a hair above absolute zero. Physicists have a term for that final state: maximum entropy, the point where no energy gradient exists anywhere left to do any work, where nothing can happen because there's no difference left between any 2 points in space for anything to happen between. No violent event marks this ending, just an ever-widening silence, matter and energy diluted until nothing meaningful happens anywhere again, forever. The second possibility runs in the opposite direction, and it needs dark energy to do something the data hasn't confirmed yet. If dark energy weakens instead of holding steady, gravity eventually gets the upper hand it lost billions of years ago. Expansion slows first, a gradual easing of the outward push that's been running the show since roughly 5 billion years ago. Then it stalls entirely, the universe reaching a maximum size and just sitting there for a cosmic instant, balanced the way a ball thrown straight up hangs motionless at the top of its arc before gravity takes back over. Then it reverses. Galaxies that have been pulling apart for the entire history of the cosmos begin falling back toward each other slowly at first. The reversal so gentle in its opening stretch that it would take billions of years before anyone watching could even confirm the expansion had actually flipped. But it compounds the way every gravitational collapse compounds, faster as the density climbs and gravity gets stronger with every step closer. Galaxy clusters that took billions of years to spread apart come rushing back together in a fraction of that time. Stars get crushed against other stars. Atoms themselves eventually can't hold their own shape against the density closing in from every direction. And everything, every particle, every scrap of structure this investigation has walked through, collapses back down into the kind of density the universe started with in its first fraction of a second. Physicists call this the Big Crunch, and unlike the Big Freeze, it has genuine drama at the end of it, a mirror image of the Big Bang running in reverse. The third option is the most violent of the three, and it depends specifically on a form of dark energy physicists call phantom energy, a version that doesn't just persist or weaken, but keeps growing stronger over time, with no upper limit on how far that strength can climb. For most of the timeline under this scenario, nothing looks different from the Big Freeze at all. Galaxies drift apart, stars burn down, the sky empties out the same slow way. Then, in the final stretch, roughly a billion years before the true end under the models that predict this outcome, the math turns violent. The outward push finally grows strong enough to overpower the gravity holding galaxy clusters together, and clusters that have stayed bound for the entire history of the cosmos come apart. Galaxies flung away from each other in a fraction of the time it took them to form their bond in the first place. 60 million years before the end, it reaches down to individual solar systems. Planets that have circled their stars for billions of years drift free, the gravitational grip between a star and its planet snapping the way an overstretched cable finally gives. 3 months before the end, the expansion force reaches down to the scale of a single planet, tearing apart rock and iron and ocean, ripping a world into loose debris flung outward in every direction. 30 minutes before the end, it reaches atoms. Electrons get stripped away from every nucleus in the observable universe simultaneously, the electromagnetic force that's held atomic structure together since the earliest moments after the Big Bang finally overpowered. And in the last fraction of a second, the strong nuclear force itself, the same force this investigation already examined as one of the 5 fine-tuned suspects, loses its grip too. protons and neutrons come apart into the quarks that build them, and every nucleus in existence disintegrates at once, everywhere, with nothing left connected to anything else. This ending has a name too, the Big Rip, and it's the only one of the three that ends in outright violence rather than in stillness or collapse. And it does it in a final 10 minutes that stand in stark contrast to the tens of billions of years of quiet drift that came before them. Here's what needs to be said plainly. Current data doesn't clearly favor any one of these three outcomes with confidence, but it does lean somewhere. The hint from 2024 that dark energy might be weakening points a finger toward the second scenario, the Big Crunch, and away from the third, the Big Rip, since a weakening dark energy is the opposite of the ever-strengthening phantom energy that scenario requires. But that hint sits at the same low confidence already flagged earlier in this investigation, barely above the threshold where physicists are willing to call something a pattern rather than noise. Nobody is confirming an ending on the strength of one survey, which leaves this case file sitting on an unsettling symmetry. The same unexplained number that let galaxies condense, that let stars ignite, that let atoms hold together long enough to build everything this investigation has walked through, is also the number quietly deciding whether everything ends in silence, in collapse, or in violence. Physics still can't tell you which. It can only tell you that whichever ending arrives, dark energy will have written it. Bring all 5 case files back into the same room, because up to now, each one has been examined the way a detective works a single suspect, alone in isolation, one interview at a time. Dark energy sitting at the edge of the vacuum catastrophe. The Higgs mass refusing to drift toward the Planck scale the way quantum corrections demand. The strong force holding nuclei together inside a window, narrow enough that turning the dial either direction erases stars or erases atoms. The matter-antimatter ratio, one leftover particle per billion annihilated pairs, unexplained inside the standard model. The flatness of space, tuned near enough to exact that any early deviation should have snowballed into total collapse or total emptiness long before now. 5 separate interrogations, 5 separate case files, each one closed on its own unresolved note. Nobody's run them together yet, so run them together. Each constant sitting inside its narrow surviving range doesn't say much on its own about the other 4, but physicists who study this stacked probability don't examine these constants one at a time when they want to understand the full weight of the coincidence. They ask what happens if you let all 5 vary freely at once, independent of each other, each one sliding across its own narrow window without any of the others holding it in place. The moment you do that, the odds don't add, they multiply. A universe that needs 5 separate values to each land inside a narrow surviving range simultaneously, with no known reason connecting any one value to any other, is sitting on odds far worse than any single case file examined alone ever suggested. This is exactly why the fine-tuning question keeps refusing to go away quietly, even among physicists who find real problems with individual pieces of the argument. Go back through the objections raised earlier in this investigation. Some of the probability language attached to dark energy rests on assumptions nobody has confirmed. Some of the naturalness reasoning behind the Higgs mass is contested inside the field itself. Grant every one of those objections full weight, and the stacked case still doesn't dissolve because the strong force and the matter-antimatter ratio don't need probability assumptions to stay standing, and neither one moves an inch once you stack it against the other 4. Even a skeptic willing to knock down 2 or 3 of these case files individually still has to explain why the surviving cases land together in the same universe, inside the same narrow window that permits structure to exist at all. That's the part that resists easy dismissal, not any single number. The fact that 5 independent branches of physics, discovered decades apart by people who weren't looking for each other, all point toward the same edge of survivability at the same time. Which brings this investigation to the rebuttal serious physicists actually reach for when the stacked odds get raised. Not a dismissal, not a shrug, an argument built specifically to answer the question this stacking creates, and it's the most serious objection this entire case file has faced yet. Here's the argument in its cleanest form. Any being capable of standing inside a universe and asking why its constants are tuned this precisely could only ever ask that question from inside a universe already compatible with that being existing. You can't observe a universe where the strong force is too weak for atoms, because there's no version of you in that universe to do the observing. You can't measure a matter-antimatter ratio that annihilated everything into pure light, because there's no observer left standing in the aftermath to take the measurement. The only universes anyone ever gets to inspect from the inside are the ones that already permitted an inspector. That deserves to be stated carefully, because it sounds at first like it's dodging the question rather than answering it. It isn't circular reasoning, and the distinction matters. Circular reasoning would be saying the constants are tuned for life because life exists, as if existence itself were the proof. This argument says something narrower and more specific. It says that whatever the full range of possible constants turns out to be, and whatever process generated the actual values we measure, every observer who ever asks this question will find themselves looking at values inside the survivable range, simply because no observer can form anywhere else.
That's not circular.
That's a filter, sorting outcomes after the fact, rather than explaining why any particular outcome occurred in the first place. This is where Weinberg's cosmological constant prediction earns its place as the strongest evidence this camp has. Before the value was measured, the anthropic argument was used to predict roughly where it had to fall, reasoning that it needed to sit low enough to allow galaxies to form without specifying any deeper mechanism forcing it there. When measurement finally caught up, the value landed inside that predicted range. Not because the argument explained the number, because the argument correctly identified the boundary any observer's universe would necessarily fall inside. Accept this reasoning fully without reservation, and it does something that deserves to be said plainly rather than softened. It ends the search. If every fine-tuned constant in this investigation is explained by the fact that we could only ever be here to measure survivable values, then there's no deeper mechanism waiting to be found underneath any of them. No hidden symmetry, no missing particle, no equation that finally derives the Higgs mass from first principles. The 5 case files this investigation has built, one by one, close, not because physics solved them, but because the selection filter renders the question of why they're tuned this way permanently unanswerable through direct observation. And that's exactly where the room splits. One side treats this as a genuine answer, the correct and final resting point for a question that never had a deeper mechanism to find. The other side hears the same argument and calls it something else entirely. Not an answer, but the exact moment physics decided to stop asking. Take everything this investigation has already established and stop treating it as 5 separate interrogations for a moment. Build one universe out of it. Not a new hypothetical with new numbers invented for effect, just the existing consequences from each case file layered on top of each other the way they'd actually stack if the dial had landed somewhere else. Nudge the strong nuclear force up past the threshold this investigation already walked through. Protons that should have waited billions of years to fuse inside stellar cores fuse instantly instead, on contact, everywhere, the moment conditions allow it. Hydrogen doesn't get the chance to persist as hydrogen. There's no slow, patient burn inside a star's core stretching across billions of years, because the fuel that powers that slow burn doesn't survive long enough to be gathered into a star in the first place. Now let dark energy sit slightly higher on top of that, the stronger setting this investigation already described, pushing matter apart before gravity gets its grip on the first clumps. Whatever debris the strong force left behind never gets the chance to gather into anything. No clumps, no proto-galaxies, no slow gravitational collapse pulling matter into the shape of a star. Just matter and radiation, spreading outward, thinning forever. Or take a different combination. Leave the strong force alone, leave dark energy where it sits, and instead touch the one number this investigation flagged as carrying no probability debate attached to it at all. Push the matter-antimatter ratio back toward perfect symmetry, the outcome every calculation says should have been the default. Equal matter, equal antimatter, annihilating completely into photons the instant they meet. No leftover billionth survives. There's no asymmetry left over to build anything at all. Not a stray hydrogen atom, not a speck of dust, not a single proton drifting alone in space, just light. An expanding universe made entirely of photons, cooling, stretching, with nothing solid anywhere inside it to mark that matter was ever present. None of these scenes need new details invented to make them vivid. They're just the same consequences this investigation already built, chapter by chapter, recombined into a single frame instead of examined one at a time. That's the point worth sitting with. Every one of the 5 case files already described what its own failure mode looks like in isolation. Stack any 2 or 3 of those failure modes together, and you don't get a stranger version of our universe. You get a universe with nothing in it capable of noticing the difference. That's the detail worth holding on to longer than any of the individual numbers. In the overwhelming majority of these variations, across every combination this investigation could construct from material already on the table, there's no observer anywhere inside the result. No physicist running the numbers. No telescope pointed outward. No mind wondering why the constants landed where they did. Just matter that never gathered, or light that never cooled into anything else, or a silence with nobody positioned to call it silence. The weight of that picture doesn't need dramatizing further. It's already sitting there plainly, in the recombined wreckage of 5 case files that all happened to survive together, in this one arrangement, out of all the ways they didn't have to. Pull back from the physics for a moment and look at the calendar instead, because the timeline of who found what and when tells its own story. Einstein wrote the cosmological constant into his equations in 1917, then spent the rest of his life treating it as an embarrassment. The matter-antimatter puzzle didn't get formalized until 1967, when Sakharov laid out the 3 conditions this investigation walked through, decades after Einstein had already died. The Higgs boson sat as a theoretical prediction for almost 50 years before the Large Hadron Collider finally confirmed its mass in 2012, and confirmed at the same time just how badly that mass refused to behave the way quantum corrections said it should. The strong CP bound wasn't tightened in one discovery. It's been squeezed decade after decade, one neutron experiment at a time, each new result pushing the allowed window smaller than the last, all the way down to the 1 part in 10 billion figure this investigation already covered. None of these people were working together. Einstein wasn't thinking about neutron electric dipole moments. Sakharov wasn't trying to explain the Higgs mass. The physicists tightening the strong CP bound across the second half of the 20th century weren't coordinating with the teams building supernova surveys to catch dark energy accelerating the universe. 5 separate mysteries, chased down by 5 separate groups of scientists working on problems that looked, at the time, like they belonged to entirely different corners of physics. Nobody sat down with a plan to make these puzzles line up. And that's the detail worth sitting with longer than any individual number this case file has produced. Nobody built these 5 problems to fit together, and yet they do. That kind of independence is exactly what makes coincidence a harder explanation to reach for, and exactly what makes a hidden unifying mechanism so tempting to chase, even without evidence that one exists yet. Because none of this is finished history sitting quietly in a textbook. Right now, neutron electric dipole moment experiments are running, hunting for the CP violation the strong force stubbornly refuses to show. Axion searches are still scanning through resonant cavities and solar telescopes, looking for a particle nobody has caught yet. Dark energy surveys are still collecting galaxy data by the million, watching for whether that 2024 hint holds up or fades into noise. The Large Hadron Collider is still colliding particles at energies nobody had access to a generation ago, still checking whether supersymmetry is hiding just past the reach of the last search. This is an investigation still being worked, with instruments running tonight, and researchers checking results that didn't exist yesterday. The 5 case files this script has built aren't closed chapters. They're open files on 5 different desks, and somewhere right now, someone is looking at a printout that might move one of them forward.
Say one of these instruments gets lucky.
Say a resonant cavity somewhere picks up a signal that survives every check, every rerun, every attempt to explain it away as noise, and physicists confirm the axion is real. What does that actually do to this case file? It closes the strong CP problem outright. The Pechet-Quinn mechanism stops being a hypothetical fix and becomes a confirmed piece of nature. The field that drives the CP violating angle to zero exactly the way this investigation described. But it does something else at the same time, because that same particle is a leading dark matter candidate. 1 detection, 2 mysteries answered in the same instant. The strong force's suspicious good behavior and the identity of the invisible mass holding galaxies together, both traced back to a single particle nobody had ever directly seen before. That's the kind of result that reshapes more than one chapter of physics on the same afternoon. Say, instead, the dark energy surveys keep collecting data, and that 2024 hint hardens into something confirmed at real statistical confidence. Dark energy isn't a fixed constant. It's a field, drifting in strength the way quintessence models predicted. That doesn't resolve the vacuum catastrophe, doesn't explain why the number is small instead of catastrophically large, but it changes the entire shape of the question. You're no longer asking why one frozen number sits where it sits for all time. You're asking what mechanism governs a field in motion, which is a different, and in some ways more answerable kind of problem. Say the Large Hadron Collider, or whatever collider eventually replaces it, finally finds supersymmetric particles, just not at the TeV scale physicists expected decades ago, but higher past, where the earlier searches this investigation covered came up empty. That doesn't hand physics a clean win either. It would mean the naturalness crisis wasn't a dead end, just a search that hadn't reached far enough yet. But it would restore the protecting mechanism the Higgs mass has been missing this whole time, the cancellation that keeps quantum corrections from dragging that number up toward the Planck scale. One confirmed superpartner, and the case file on the Higgs stops being an open mystery and starts being a solved piece of the puzzle with a name attached to the solution. Here's the honest part though. None of these discoveries alone or even together would fully resolve the fine-tuning question this investigation has been building. Confirm the axion, confirm shifting dark energy, confirm supersymmetric particles at some higher scale, and you've still got the matter-antimatter ratio sitting there, with no mechanism proven. You've still got the flatness problem resting on an inflation model that some physicists argue just relocates its own fine-tuning rather than removing it. Each discovery removes one card from the stack. It doesn't collapse the stack. Full resolution, the kind that closes every case file at once instead of one at a time, would need something none of these individual wins provide. It would need an actual working theory of quantum gravity, the seam this investigation already identified between general relativity and quantum mechanics, finally stitched shut. Physics has been chasing that seam for a century. Nobody has closed it yet. Earlier in this investigation, we asked why the constants sit inside a narrow range instead of anywhere else. And this whole case file has been built on the assumption that this question has an answer sitting out there, waiting to be reached. Here's the boundary that assumption runs into. Every observer capable of asking why the constants are tuned this precisely is only standing there, asking because the constants already allow that observer to exist. That's not new information at this point in the investigation. What's new is what it does to the search itself. Once you stop treating it as an argument about coincidence and start treating it as a limit on what can ever be observed, because the filter this investigation described earlier doesn't just explain why we find survivable values. It restricts every future measurement anyone will ever take to the same narrow range permanently. By definition, you can build a more precise neutron electric dipole moment experiment. You can push the axion search across a wider slice of parameter space. You can collect another decade of dark energy surveys. Every one of those instruments will still be operated by an observer who can only exist inside the surviving window, taking measurements from inside the one range that permits the measurement to be taken at all. That's the deeper unease sitting underneath everything this script has walked through. It's not that physics lacks the tools to find a cause behind the tuning. It's that the position from which physics looks may be structurally incapable of distinguishing between two very different possibilities. A universe where these constants have a hidden cause nobody has found yet, and a universe where they have no cause at all and simply are what they are because nothing else could have produced an observer to ask. Both of those universes look identical from inside the narrow range. Every experiment this investigation has cited, the LHC runs, the axion searches, the dark energy surveys, gets performed by someone who can only ever confirm that the values permit their own existence. None of those experiments can step outside that condition to check. Say this plainly so it isn't mistaken for giving up. This isn't defeatism, and it isn't an argument that physics should stop running the experiments already in progress. Every avenue this case file has covered, supersymmetry, the axion, shifting dark energy, quantum gravity, remains worth pursuing, because each one could still close a case file, even if it can't close all 5 at once. What this is, instead, is a boundary condition on what the scientific method can access from where it's standing. Science works by observation, and observation requires an observer, and every observer available to do the observing is filtered through the same narrow range this whole investigation has been describing. That's not a flaw in the method. It's a wall the method runs into, honestly, without anyone having built it on purpose. Which is exactly where this investigation has to land its closing argument. 5 constants. Say them one final time, plainly, with nothing new added. Dark energy, the Higgs mass, the strong nuclear force,
The matter-antimatter ratio.
the flatness of space. That's the whole case file. The same 5 suspects, named at the very start of this investigation before any of them had been explained. Here's the finding, stated as directly as this script can state it. Every calculation physics currently has access to says this exact combination shouldn't have produced a universe capable of forming galaxies, stars, or anyone able to study them. Not one of these constants alone. All 5 together, landing inside the same narrow surviving window, at the same time, with no confirmed mechanism connecting any of them to each other. That's not a hunch or a talking point built for effect. It's what happens when you run the numbers honestly, using the same physics that puts satellites in orbit and predicts particle collisions to a dozen decimal places. Physics has answers on offer, just not one answer. There's the anthropic argument, the position that says we shouldn't be surprised to find survivable values because no observer could ever measure anything else. There's the search for a deeper mechanism, supersymmetry, the axion, shifting dark energy, each one still being tested in a lab or a survey somewhere right now. There's the objection that some of this fine-tuning language rests on probability assumptions nobody has confirmed, which weakens some of these case files without erasing the strongest ones. None of these positions has won. None of them has been ruled out either. Ask 10 physicists which explanation is correct, and you won't get the same answer twice. That's not a failure of the field, and it shouldn't be dressed up as one. It's what an active investigation actually looks like from the inside, before the case gets closed. Physics doesn't owe anyone a tidy resolution just because the question has been sitting unanswered since Einstein first scribbled a fudge factor into his equations. Some mysteries take a generation, some take longer. This one has already outlasted every physicist who first noticed a piece of it. So here's where the numbers sit, right now, tonight. Still there. Still unexplained. Still being measured by instruments that don't take a night off cavities, tuned to catch a particle that might not exist, detectors buried in mine shafts waiting for a neutron to show the wrong number, satellites logging galaxy positions by the million. Somewhere, at this exact moment, a researcher is looking at a printout, or a plot, or a column of numbers that just came in, checking whether it's noise or whether it's the next crack in this case. Nobody knows yet which one it is. That's what leaves this case file open instead of closed. That's where this one has to end, because that's where the physics actually stands. Not solved, not disproven, sitting on a desk somewhere, waiting on the next data set.